So, Frederic, I first want
Yes.
to welcome you for being here. It's the first day of the Ivan Pulse, and Frederic is joining us from Tokyo. So, in Tokyo, it's right now, it's midnight. So, thank you so much, Frederic, for joining us at this ungodly hour. And just as
No
a
problem.
Uh, so Frederic is a game designer in the game industry in Japan. He has worked at Square Enix, and there he specialized in NPC and anime AI. Right now, he is at K-Lab in Roppongi and working with research and IP development. He's also just about to finish a PhD thesis about gaming. But that will probably happen later. And today, Frederick is going to give us a short history of gaming. So I'm so happy to have you here. Welcome, Frederick.
Thank you very much. And I guess you said everything for the introduction, so I guess I can go directly to the lesson. I'm not sure I can go through history of game AI in general. So let's say that we try to go till the end of the 80s, beginning of the 90s, and if we have some time to discuss the rest, we will. Okay? Okay, so let's start. So basically, so if you try to think what is the first video game in history, I'm pretty sure many of you might have this image in mind. Many of us think that Pong is the first video game in history, and it's wrong. It's not Pong. And some of you might be more in the right and think of this one, which is Tennis for Two. And well, you might be right, but not exactly. It's not exactly the first video game in history neither. The first video game in history is actually the Nematron. So the Nematron was something that was presented at the World Fair in New York in 1939, and that was a machine that was able to play the game of Nim. So it's kind of a mathematical game where you have to be the last one to remove the a matchstick normally. So you play that with matchstick, and you have to avoid to have one matchstick left. And basically, this Nematron was running on an analog computer. And it had an AI adversary, actually a very good AI adversary, because there's a pattern in NIM that allows you to be almost unbeatable. And it was presented then at the 1939 New York Fair. But the most accepted first video game in history is probably Tennis for Two that I talked about earlier. And Tennis for Two, if we look at what I was saying about Tennis for Two is that it was running on an analog computer and had a simulation of gravity. So basically, it was using the analog computer to calculate the parabola of a tennis ball. And on the other side, you have here a game that precedes Tennis for Two, but that is not fun, which is OXO, so which was like an AI for tic-tac-toe. The thing is that this AI for tic-tac-toe was just a pattern AI that was implementing the optimal technique for tic-tac-toe, so you could not win against this AI. So I don't think that really counts as a game. If it's not fun, you cannot win. On the other side, the Tennis for Two was fun to play. You could not really count the points or whatsoever, but And here you can say there's a form of AI also, because Tennis for Two has, this gravity simulation, and this gravity simulation is in a way a form of AI. If we consider today some form of animation techniques, etc., in video games, some form of AI, then this gravity simulation in Tennis for Two is a very simple form of AI. And just for context, let's look at what phone and what we were listening to music on was like during those years. Then, so before the 1950s, AI was already being uh, thought of around games. And so in a way, it always was about games. And this is thanks to a man called John von Neumann, who's the inventor of the computer architecture as we know it today, and who's also the inventor earlier of game theory. So game theory, which has been used thoroughly later for economics, but which originally was really about games. And game theory is about finding the best strategy to win at any game. So basically, just for context again, that's what a phone and a phonogram looked like in the time he theorized game theory. And game theory really is just a minimax algorithm. I guess that many of you already know what is a minimax algorithm, but minimax algorithm is a way to minimize for one player a score at a game, if it's a two-player game, and maximize for the other. And if you do that at different depth of a tree of different possibilities of a game, then you can choose the best, the least, let's say, the least bad option for one player, because you take into consideration that the other player will take the best option for himself. So you minimize the score for one player, you maximize the score for the other player. And that was basically all there was about the game theory of von Neumann. And from this theory of von Neumann, other researchers will start to theorize on how you could make a computer play a game. And one of the famous examples is David Champanoni and Alan Turing, who together thought of a paper machine. Basically, they didn't have a computer back then. So we are in 1948. So in 1948, Turing could not put his hands on a proper computer. He thought about later maybe get a Ferranti Mark II in order to try his, or Ferranti Mark I at the time, in order to try his algorithm, but couldn't yet. So he decided to play the computer himself. And as the computer, so he tried to create an algorithm to play chess with his friend David Champanoni. And the fact is, this game was recorded, and many tried to reproduce the algorithm that he might have used. But the fact is that Turing actually kind of cheated at the end and didn't use the algorithm that he intended to use when he was playing the computer. He was still a human after all. And but the idea was there that you can make an algorithm for playing chess, where here Turing was just calculating every move of the computer. But basically, yeah, you have like two types of agents in a way in game AI history. You have game playing agents, like the ones that Turing and Champanoni were trying to build, and you have video game agents. And game playing agents are really only for the labs at the time. So here you can see Dietrich Prinz, that after Turing's death, I think, could start to implement chess algorithms on a Ferranti computer. And but he discovered that he could not really implement a full game of chess. So basically, he tried to make the computer play end games, try to find the right move to end the game in a victory. And so that's kind of how this kind of like a chess playing engine started. On the other hand, you have like here Arthur Samuel, who was is considered today as the inventor of machine learning. Arthur Samuel thought, well, I can use, yes, the minimax algorithm. I can also make the minimax algorithm a little bit less wasteful. So he decided to basically cut the options that he knew would not lead to a good move. And so that's what we call alpha beta pruning. And he pruned the bad options. He used the minimax algorithm. And on top of that, he decided that at every game that his agent would play, it would be able to record deeper and deeper its progress through the tree of the game of checkers. This time it's not chess, it's checkers. And basically, the more you would play with the agent that Samuel created, the more it would get better, but very slowly because it would have needed hundreds of years in order to completely explore the tree of the game of checkers. But still, it was getting better, and a medium player would have kind of difficulties playing against the AI created by Arthur Samuel. And also, you can think of dialogue as a kind of form of play, and many laboratories tried to make conversation agents, often based on a kind of illusion. So there was basically two very famous agents back then in the 1970s. One was Elisa. Elisa was supposed to be a kind of a psychotherapist, so psychiatrist AI. So she would always like ask questions, are you feeling okay with that? Or things like that, and never really saying anything concrete. And on the other side, Paris was an agent that was supposed to imitate a schizophrenic, paranoid patient. But when you were making them discuss together, everything crumbles because both of them are just like reflection agent that just like send back what one sends to the other, and it just crumbles apart. But they tried to make Eliza and Paris talk together on the ARPANET in 1972. For video game agents, so the game agents that are in the video games that we play, the consumer games, the story is a bit different. So in the 1970s, basically, you had no AI, only two-player modes for most games. So basically here I give the example of Pong. There has been versions of Pong with opponents, AI opponents, but they were re-releases of the game later. In the 1970s, you could only play Pong if you had someone to play with you. So that's why there's always two of those little potentiometer to control the position of the racket. And still for context, that's what a radio looked like during those years. But later in the 1970s, in Japan, like some more interesting things started to emerge. And you have here the example of speed race. Look, yeah, the sound this time is low. But basically in speed race, you have like other agents that are placed on the road in front of you. Of course, it's just like randomly placed. and they can like move from left to right, and you have to avoid them. It's really simple, but it's a start for AI agents. A bit later, you start to have something really interesting that starts to emerge, and Sprint 2 by Atari is a very good example of that. In Sprint 2, you already have pathfinding. So here, the two gray agents here are using some kind of pathfinding to find their way on the circuit. Okay, I mean it's 1976. It's crazy, like already pathfinding, and we will not find pathfinding in many games all across the 80s. There will be only very few games that have pathfinding. And this is thanks to a very clever system that was simply putting like a vector field on the entirety of the track so that the racers would always know where to turn. And it's something that would be a very clever way to make a massive pathfinding in some of your levels, even in the games you implement today. Then America lived through two consecutive video game crash. Once in 1977, because there was too many copies of Pong that were being released. People didn't understand that what made the video game industry was not the hardware, but actually having more software. But everybody was making Pong clones in 1977. And in 1984, there was a second crash also for too many games that were of low quality and that did not satisfy the public. But in parallel, in Japan, people were dancing on music like that. You have anime like that were on the TV with robots at the center of everything, and people were playing those kind of games. So you have Space Invader that started to implement pattern AI with like the aliens that were moving from left to right and down towards towards the player while shooting at random, while the first row was shooting at the player at random. And only a year later, you have something as beautiful as Galaxian with like the spaceships that were aiming for the player with a bit of sliding motion so that you can still avoid them. But it's quite impressive for the time. And just for context, in Japan, that's the year that the Walkman was released. In the 1980s, we saw the birth of AI aesthetics and personality. Here, Toru Iwatani is also the creator of Space Invader. Came back with something really interesting with Pac-Man. Okay. So here, as you can see, the different ghosts are moving in different manners. Okay. So they all have their own personality, right? Oh, it doesn't get you. But anyway, and in order to implement those personalities, basically, Iwatani worked in a way that was like he organize the game around a finite state machine. So basically, the ghost could be in different states. You have a scatter state at the beginning of the game where the ghosts go at the four corners of the maze, and you have pursuit state where the ghost will try to go after Pac-Man, and you have the Pac-Man invincibility state, so the frightened state for the ghosts, where the ghosts will move in a pseudo-random way. And basically that's and the state where they return home when they've been eaten by Pac-Man. And basically, you have like four different AIs for the characters. So basically, Akabe, the red ghost, is always targeting Pac-Man. In a way, so the position of Pac-Man is the position targeted by Akabe. Pinky is always targeting in front of Pac-Man. So you like two squares in front of Pac-Man is the target of Pinky. Okay. The thing is, because of an overflow bug, when Pac-Man is facing up, the position of the target will move by as many blocks on the left. And this bug will also appear, for example, in the AI of Aosuke. So in the AI of Aosuke, you have Akabe that is looking in a certain direction, and depending on the direction where Akabe is looking, Aosuke will always try to target two blocks away from the intersection with Pac-Man. But the problem is that here also you have the same overflow bug as with Pinky when Pac-Man is looking up. So this intersection is actually moving slightly on the left. And Guzuta is making basically a calculation of the Euclidean distance with Pac-Man. And if he enters the Euclidean distance of Pac-Man, he returns to scatter mode. But if he's out of the Euclidean distance of Pac-Man, he will target Pac-Man. So basically, when Pac-Man gets close, he gets away. And so basically, you have this way, like personality expressed through the use of AI. And everything, but the thing is that everything was so deterministic that many players ended up learning by heart the patterns of those AI, which is in a way a good thing for a video game because it makes the video game fair. But you had only one place where randomness was implemented in Pac-Man, and it's when the ghosts are in frightened mode. So in frightened mode, the ghost will choose their path. They can go back on their path, which they can't do when they are in normal mode, and they can like move in random patterns. And but back then, random number generators were not a thing. Like you couldn't have real randomness, so you had to find ways to make random generators that would be deterministic. And so, for instance, Pac-Man alternates multiplication by 3 and by 5, and alongside with some increments by 1, and it gives the illusion of randomness. In Final Fantasy I, Nasir Gebeli, the main programmer, just implemented a finite lookup table and would just like go through the numbers of the lookup table one after the other, and that would be his random generator. But yeah, the absence of real random generator also made it easier for players to learn patterns sometimes. Not really in Pac-Man, but in some games it might become possible. Basically, in early fighting video games, such as Atari's Boxer, you had to play with someone else in order to play a fighting game. and even like karate for ultravision. Here again, it's something where you have to play with someone else. So the image of fighting games where you have the arcade mode, where you have to face many AI players at the beginning of the 80s was not yet a thing. So in the beginning of the 80s, Jordan Mechner was saying that he was often quitting games because he started to get bored in a way of playing over the same theme over and over again. And it's probably what motivated him to use, in a way, the illusion of animation in order to make more interesting behaviors in his games. And
footage. So I got my dad and my sister to model this footage.
And here you can see that he recorded on Super 8, like karate pose.
I also filmed myself running,
etc., with his family members.
That footage didn't look so good, so I didn't use
it. He copied them on paper, on tracing paper, and then he input like every pixel value one by one on the keyboard in order to make his sprites. And the result was Karateka. Okay, and Karateka, it's just a simple state machine again, right? So it's just characters that are entering different states, maybe with some probabilities, sometimes maybe a fake random number generator, but simple state machine. But it works because the animation gives a kind of soul to the AI. You have to think that tools for computer graphics back then were scarce. So the apparition of tools for computer graphics really changes in a way. So in the middle of the 80s, changes the type of AI characters that we start to see appearing. And thanks to the apparition of early computer graphics tools, so for example, Jordan Mechner would be able to make Prince of Persia in 1989, and but also games like Street Fighter 1 would become possible because now it was possible to draw on a computer, and drawing on a computer can make appear a simple state machine as if it has some form of soul. Basically, in the 1970s to the 1980s, simulation became something important. And I think that one of the epitome of simulation in AI is the use of automata. So cellular automata. So once again, we have to thank von Neumann for one of the first ones, which is his self-replicating automata. So von Neumann wanted to prove that AI could lead one day to creating machines that can self-replicate. And so he created an algorithm that was a cellular automata that was able to self-replicate. Inspired by von Neumann, later Conway would create the game of life. So the game of life it's really, really simple. You have only a few rules that would dictate if a cell can live or can die according to the number of alive neighbors that it has. So you can start with a seed. So you draw something on the board of the game of life, and then when you run the algorithm, so one cell dies, another one resurrects, etc., and it creates patterns that look like life. And the idea with simulation like this is that you have a system that can maintain itself only on the basis of rules. For example, the Langton's loop is also able of self-replicating, just like the von Neumann algorithm, and there's been variations on the Langton's loop. So I really invite you to look at these things. But it's something that we have not seen often implemented in consumer video game, but that probably is the precursor of the many simulation games that we saw appear in the 1980s. So from the mid 1980s, we have simulation games like Little Computer People. So Little Computer People is working entirely on a stochastic state machine. So a stochastic state machine is a state machine that works on probabilities. So you have a certain probability that your character will decide to climb up the stairs and go to play his piano. A certain amount of probabilities that your character, after playing the piano, will want to watch the TV, etc., etc. In this game, you would have a different character according to the actual physical copy of the game that you bought, because basically the first bytes that were written on the disk of the game represented the parameters for this stochastic state machine, and you could have like literally millions of parameters that would create millions of different versions of your little computer person. And so if you were comparing that with a friend that has his own little computer person, the personality of those two would appear greatly different. And then you have like simulations like SimCity. So here it's more about creating a huge system that is made of many variables that influence each other. And basically, in SimCity, the closeness, for example, of a nuclear power plant would have impact on the taxation levels of this district that you can raise, basically. And so basically, you cannot raise so much tax if you make people live just next to the nuclear power plant. And also, it has impact on pollution. It has impact on many other factors, and all those factors are influencing each other. And the fun in a game like SimCity is to see where the simulation is leading you. Hey, if I try to do this, can I get to a situation that would be positive for my city? Can my city survive if I make those choices? And basically, it's the only fun there is, and there is no other rules than that. And Populus, the god game from Bullfrog is based on similar premise, basically. So really, the idea of simulation started to be kind of a guiding principle for many computer games in the mid to late 80s. Another thing that will emerge in the late 80s is the idea of an adventure where you have companions. And I was kind of surprised when making my research to realize that there was almost no games with companion AI in most of the 80s. And you would have two-player games. You would have games with opponent AI, with enemies that pop at a certain position, but don't follow you for too long. But games where a companion would follow you all along your adventure, this only appears at the end of the 80s. And basically, even in games like Ultima, for example, you would not see the team members of your character, like your team, appear on the map. You would have description of your characters in Western RPG. Well, in Japanese RPG, while they are generally more authorial, more story oriented um, than Western RPG, it seemed more important to have those characters, those actors of the story being displayed on the screen and being following your characters while they are there. And in 1988, you have a game by Kure Software Kobo that is called First Queen, and another game that the same developer released the same year is called Silver. Oh, sorry, I forgot the name. You'll take a look later at the history of this this developer, but basically where you could have like literally 20 characters that would follow your main character on screen with some form of pathfinding. It was definitely not yet A-star pathfinding, but it was working. You had your characters following you on the screen there. Then you have kind of the explosion of companion AI at the end of the 80s. So you have games like Shadow Dancer. So in Shadow Dancer, you have your dog that follows you and can act independently. But basically, the dog is kind of following your actions with some delay. And sometimes the AI has to bring back the dog next to you when the dog gets stuck. So still pretty much state machine based. You had Strider, where you had like a flying robot that would always come with you. The technique of the flying robot is something that we still see in many games today that don't want to deal too much with the difficulties of moving an AI through the video game space. Or you had the boy and his blob, where you had a bunch of contextual actions that you could do at different places that would make your blob move with you in different situations. Then, in the beginning of the 90s, you will start to see appear more complex following AI characters, like companion AI behaviors, where the idea was, and what if player 2 was an AI? And really the first time you start to see this idea being put into development is in Sonic the Hedgehog 2. In Sonic the Hedgehog 2, you have the possibility to basically play as Sonic and have what would normally be player 2, so Tails, being controlled by an AI. But it's still very simplistic. So basically, Tails kind of follows your actions, and Tails is brought back by flying back to you with his helicopter tails. This is clearly a crutch in order to make Tails seem like he's playing with you, while it's still a very simplistic AI implementation. But where it starts to be impressive is with two games of 1993. One is a British game called The Chaos Engine by the Bitmap Brothers. Here, you're basically shooting at enemies, and it would be a two-player game normally, and you have one player controlling one character, the other player controlling the second character. But if you're playing alone, the second character is controlled by the AI. And here, the character will follow you all along your adventure, all along the levels that you're crossing, and will be able to shoot enemies and to do most things that the player 2 would be able to be doing. And actually, in a book that they released recently, the Bitmap Brothers, the studio that was in charge of it, said that they actually implemented a kind of Turing test in order to see if their AI was good enough. So basically, they would not tell a player if they were playing with someone or with the AI. And from the moment that the answers were like 50% wrong or 50% right, they decided that it was good enough for them to release. On the other side, you have Secret of Mana, which was designed for AI. So basically, Nasir Jebeli, the programmer from Squaresoft back then, decided to make this game centered around the idea that you will have an RPG adventure where you will meet different characters one after the others, and they will start following you all along the adventure. And you have moments here in the game where the characters will follow you in caterpillar manner. So that was the easy way to do to avoid doing proper pathfinding. And when there's enemies, the characters will scatter and go towards an enemy, fight them. And when all the enemies are dead, they go back in caterpillar motion, basically. One thing that starts to be increasingly important during the 90s is the use of pathfinding. So basically, especially in strategy games, real-time strategy games, it was really important to be able to click somewhere and have your unit move on the map, avoid the obstacles or avoid other units, etc., in order to move on the map and go to the place where you clicked. Okay, and in order to do so, games had to start implementing pathfinding algorithms. So among the pathfinding algorithms, you could have like a star, or you could have the Dijkstra algorithm. As you can see, Dijkstra is kind of trying too hard, so we'll try to explore the entire tree of possibility, while the A-star algorithm is kind of operating with some pruning, and through this pruning, we'll be able to find not necessarily the shortest path, but we'll find a path more easily. While on the other side, Dijkstra here is slower and will allow you to find a shorter path than what A-star would be able to find. Most games will choose A-star because it's a fast algorithm that you will be able to run on a click of a button. Later in the 90s, some experiments will start to be done with neural AI. I know it may be surprising that in 1996 we had a game that implemented neural AI, but it's the case. So a game like Creatures. So in Creatures, you had these little monkey-like characters that would be able to perform actions, go to eat, like say fake sentences and things like that, simply on the basis of having a 4-layer neural network that has about 952 neurons and 5,000 connections. And the idea behind Creatures was that as the player would interact with the neural network, the little creatures would start to learn. In reality, it would have needed way more training in order to to start seeing behaviors really emerge. So it was kind of like they often appeared a bit stupid, but the game was really pretty, and some people found it fun to torture those poor creatures. Yeah, so Creatures was one of the earliest experiment of using neural networks in a video game. I jump a bit through time here, but in the mid 2000s, started to see planning AI being implemented in video games, and basically through what we call goal-oriented action planning. So goal-oriented action planning actually uses strips. So strips is an algorithm that was developed by Stanford Sale, if I am not mistaken, and in the 1970s, basically strips was used to control a big robot that would be able to choose its own actions and plan for different goals of actions in a room. And the robot was called Shaky because it was so big that it would like move like this and be all shaky. And only in 2006, we would have a game that would implement an equivalent of strips for its character AIs. So in Fear, you have characters that have a very simple state machine where they can do a smart action, like use a smart object, go to, and so sorry, I have a hole. But anyway, they basically had like only three actions that they could perform. But this, so perform action, use smart object, and go to. And basically the perform action was like performing a certain number of contextual action that they could do. These actions would be determined by the search through a possibility space. So basically, you would use the A-star algorithm, the algorithm that we saw earlier here, you see. So we use this A-star algorithm, but instead of using it in space, we use it in possibility space. So basically, you use it through different versions of a game state. And when you do that, you can perform quite fast search through all the possibilities of a game state and have like a commando behave as if they coordinated their actions and that they come for you, and that basically for real in Fear there was no communications between the agents, but the fact that the agents had access to the game state and could search for the best plan of actions through the game state, they would start to have behaviors that would emerge that would feel like they were a coordinated commando. And then you add some voices on top of that, and it feels like they're communicating with each other. And to just finish with like some recent use of neural machine learning, we can maybe look at what Sony is doing with Gran Turismo Sophie. And so basically Sony is training one of its cars, of its AI in Gran Turismo 7 based on simulation data, and would use reinforcement learning in order to make an AI that is really, really good at driving cars. Given that Sophie is the Gran Turismo 7 AI, Gran Turismo 7 is famous for being one of the most realistic car simulators. So basically the goal of Sony with this AI is to bridge the gap between video games and reality and have an actual self-driving car for racing that would be controlled by Sophie. And I think I will stop the talk here and have your questions. Of course, this is like a tiny part of what I could have said about the history of video game AI, but I hope that you enjoyed the talk. Thank you very much.
Thank you so much, Frederic. How is it in the room? If you say your question, I will kind of repeat it in case that is needed. Like in game companies in the team, when it comes to the programmer or the team as a full thing, how much effort and resources is put on AI in terms of manpower or person power?
Oh, this is the sad question of like basically, but I hope this will change. But basically, graphics take the most of the budget in a game. Graphics, animation. So if your AI is related to animation, then yeah, you might have some budget. If your AI is purely behavioral, you might end up alone working on it, even on triple A games, or you might end up in a 2 or 3 person team at most. But I think it will change because AI will become a more important part of marketing in the years to come, and so don't get discouraged by what I say just now, because this is a talk of the past in a way, and things are getting better, and more is invested now towards AI. Is there anyone in the room that is interested in making it their job to either become a AI programmer or become a AI game designer? Like, because I think it will become a job that will become more and more important. We have so often AI has been considered over the years as only a programming matter, but it touches so many fields. So basically, you have to know a bit about like behavioral sciences and things like that in order to make uh, interesting AI, where it will more and more be necessary to have also designers that are educated about AI. So is there anybody who's interested about?
Just I'm kind of interested in exactly just AI game design and behavioral patterns, making things feel super especially like the early Pac-Man days. Because I think it's interesting since you don't really realize it unless you dig deeper.
Did you hear that comment?
Not entirely, I'm sorry, because it's a bit.
Yeah, exactly. And it was a bit of a long comment, but the comment is like the interest of looking at behaviors that feel lifelike and pseudo-random. I'm sure I'm completely butchering what
No, no.
I'm trying to say, but
I think I get what he means. So if I have an advice, it's like, don't hesitate also to look at those examples like Pac-Man and all those old games that managed to make you believe in AI, where there was basically just a state machine. Because it's often in Pac-Man, I would say that the secret is the fact that there's 4 of them. The fact that you can see them behaving differently makes you project more about those characters than if the 4 were behaving the same way, or if like you had like just one AI model, or if they change sometimes the amount of sameness. For example, in Miss Pac-Man, that's what they do. So in Miss Pac-Man, the AI is in a way complexified for the ghosts, but it makes them feel more machine-like. because the clear caricaturization of their behavior in the original Pac-Man is what makes them feel alive to you as purely on a storytelling point of view. Of course, in Miss Pac-Man, it made the game more difficult, but it killed a little bit the characterization of the AI of Pac-Man.